Boa tarde a todos. Inicialmente eu queria agradecer a presença de todos e informar que é um momento muito importante nos eventos de comemoração dos 60 anos da Faculdade de Medicina. Hoje nós temos um convidado que é Prêmio Nobel, o professor Murad, certo? Para apresentá-lo, eu quero convidar o professor Gilberto Denucci. O Gilberto Denucci é formado na casa, ou seja, é colega nosso, da turma de 1981. O professor Gilberto vai fazer a apresentação do professor Murad.
Bom, Fernando, muito obrigado. É uma honra muito grande estar aqui na Faculdade de Medicina de Ribeirão Preto e apresentar o professor Ferid Murad. É um momento agradável porque o professor Ferid Murad não é a primeira vez que ele vem a Ribeirão Preto. Essa é a segunda vez que ele vem a Ribeirão Preto. Eu o trouxe a Ribeirão Preto em meados da década de 90, quando ele ainda não era um prêmio Nobel. Ele tem bastante colaboração conosco, com o Brasil. A primeira vez que o professor Murad veio foi em 1990. E a minha relação com o Fred começou em 90, porque eu morava na Inglaterra antes disso. E quando eu fui trabalhar com o professor John Vane, eu tive um aluno de doutorado, que era o Tim Warner, e contratei uma técnica de laboratório, que era Jane Mitchell. Essa técnica, depois de um ano, eu convenci o John a registrá-la como aluna de doutorado, e hoje o Tim Warner é professor do St. Bartholomew's Hospital Medical College, da Universidade de Londres, e a Jane também é professor no Imperial College, que é um dos colleges mais importantes lá de Londres. Ambos depois fizeram doutorado conosco, foram fazer o pós-doutorado com o professor Ferid Murad. E daí surgiu a nossa colaboração. Ele esteve no Brasil em 90, esteve no Brasil em 95, depois nós organizamos a primeira reunião de óxido nítrico, que foi em 1999. Na verdade, a reunião começou a ser organizada em 98, ele também não era prêmio Nobel ainda, mas é assim mesmo, ele ganhou o prêmio Nobel e veio para a reunião. E depois eu tenho tido várias outras colaborações com ele, em termos de mandar alunos de postdoc e receber alguns colaboradores deles. Fred, it's a great pleasure to have you here at the medical school, and we're looking forward to hear from you.
I'm pleased to be here today. I guess I need to be careful getting too close here to the microphone. I'm from the United States, and I think I brought the global warming to Brazil. I understand this is the hottest day you've had this year. It's as though I'm visiting the Middle East again, where it gets pretty hot. But what I wanted to do is tell you about cell communication, cell signaling, as I call it. It's an area where I've worked my entire research career. I knew when I was a youngster that I wanted to go to medical school. I was about 10 or 12 years old. I said I'm going to plan to become a doctor. And then as I finished college to go to medical school, there was a new program beginning in Cleveland at Western Reserve University that permitted you to do both a medical degree training and a PhD degree training. And instead of 4 years of medical school, it was 7. And I decided that's what I would do. And my fiancée was surprised because we wanted to get married, and she was prepared for 4 years, but not for 7. My parents were hoping that I would become a doctor and go back home to practice medicine in my hometown near Chicago. And I said, no, I'm going to become a scientist and a professor now. And I think they were disappointed, but they didn't say anything. And I thought, how do I tell them what I'm going to do? And I said, if I become a doctor and go home in my entire lifetime, maybe I can help 2,000 or 3,000 people. If I go into science and I'm lucky, maybe I can help more. And then they understood. And it's really exciting to look back and realize that my research has probably helped millions of people. And that's very rewarding and exciting. And I think that's why most of us go into medical research. The notion of cell communication is really an old concept. In the late 1800s, a physician in the state of Michigan in the United States, Beaumont, had a patient with a hunting accident with a gunshot wound to his abdomen. And the patient developed a fistula from his stomach to the exterior. And he noticed that whenever his patient would see or smell food, he would enhance his gastric secretion through this fistula. Well, this attracted the attention of Pavlov. Pavlov was a physician in St. Petersburg, Russia, interested in gastrointestinal physiology. And he developed his very famous dog model, the Pavlovian dogs. He created pouches and fistulas in his dogs, and when he showed them food, and they could see it and smell it, they enhanced their gastric secretion into the pouch or into the fistula. And he did this over and over and over again. But then as he showed them the food, he rang a bell. And he repeated the process many, many times to the point where he conditioned the animals such that he didn't have to show them food anymore. He just rang the bell, and they enhanced their gastric secretion. This convinced him that the senses, vision, smell, the brain, were somehow talking to the stomach and regulating gastrointestinal physiology. For that work, he received the Nobel Prize in 1904, understanding gastrointestinal physiology and the relationship of the nervous and sensory systems. That was 4 years after the Nobel Prizes began in 1901. Today we know that lots of cells in the body talk to each other. It's a very common phenomenon. And that's how I began my research as a student, a PhD, MD student, showing that hormones like epinephrine and glucagon regulated cyclic AMP production, which was discovered the year before I joined Earl Sutherland's laboratory. And they were interested in how these hormones regulated liver metabolism and phosphorylase activity to degrade glycogen to make glucose. And my assignment was to figure out if the effects of catecholamines were mediated through the alpha adrenergic receptor or the beta adrenergic receptor. And that was an easy assignment, actually. It only took a few months to do those experiments. But it turned out to be a very important set of experiments. We learned that they were mediated by the beta adrenergic receptor, and that's how these receptors were coupled to cyclic AMP production to increase glycogen degradation. And I continued that work into smooth muscle models in the heart and a variety of other tissues. We also found that other hormones, such as the cholinesterase, the muscarinic agents, inhibited cyclic AMP production. And what an exciting time that period was, that 7 to 10 year period, looking at all of these hormones that were working through cyclic AMP. ACTH, antidiuretic hormone, a long, long list, gonadotropins. And in 1963, 7 years after the discovery of cyclic AMP, a couple of chemists gave inorganic radioactive phosphate to rabbits. They harvested the urine, looking for organic phosphates in the urine, and found two major organic phosphates, cyclic AMP, and the other was cyclic GMP, guanosine monophosphate. These compounds are slightly different from each other based on the position of the amino group on the purine ring, but that was the first description of another cyclic nucleotide as a natural product. And some of us said perhaps cyclic GMP will be another intracellular messenger to mediate the effects of various drugs and hormones. And that hypothesis turned out to be true. And I'm going to lead you through this thinking and some of the early work and how this work has evolved to discover yet other messenger molecules, nitric oxide is a very important one, and how it relates to today's medical research in biology. And let me start with this cartoon to show you the concept. These are three different cell types that are going to communicate with each other. I'm going to call cell type number 1 a neuronal cell. It could be a central neuron in the brain, or it could be a peripheral neuron in a nerve terminal somewhere in your arm or leg or somewhere else. Cell type 2 is an endothelial cell lining the wall of a blood vessel, much like an inner tube in your tire, very thin, one cell thick lining in the blood vessel. Cell type 3 is a smooth muscle cell in the wall of that blood vessel. It controls the diameter of the blood vessel and therefore the delivery of blood and oxygen and nutrients to tissues downstream. They're all going to talk to each other. Cell type 1 produces a substance that it releases into the bloodstream. If it comes from a neuronal cell, we call it a neurotransmitter. If it's an endocrine cell, we call it a hormone. If it's an immunologic cell, a macrophage, or a T cell or thymocyte, we call them cytokines and growth factors. They're given a variety of names. There are hundreds of these messenger molecules. Earl Sutherland called them first messengers. Hundreds and hundreds. Some are simple amino acids. Some are peptides. Some are lipids, like the eicosanoids, the prostaglandins. Some are large proteins, like the gonadotropins. In the bloodstream, they often tag on to some carrier protein to protect them from degradation and inactivation. Sometimes they're in the circulation free without these carrier proteins. And they home to go find their target. They're searching for their target. And they identify their target by the presence of a protein in the wall cell membrane of the target cell that we call a receptor. These are integral membrane proteins, and the first messenger, or ligand as we often call them, interacts with this receptor in a three-dimensional conformational fit, like a key in a lock, like O.J. Simpson's hand in the glove during the trial. It didn't quite fit, but he got away with it, right? This interaction permits the biochemical machinery in the cell to take over to make an intracellular messenger that transmits that information into the nucleus or into the proteasome or into the mitochondria or wherever in the cell. And the first messenger doesn't necessarily have to go inside of the cell. Now, sometimes it does with steroid hormones, thyroid hormone, a few others, but most often it just interacts with a receptor in the membrane. The first such intracellular second messenger was cyclic AMP, discovered in 1957. Since then, there are a handful of other messengers: cyclic GMP, calcium, diacylglycerol, some of the eicosanoids, the prostaglandins, some of the peptides, and my favorite is nitric oxide. Nitric oxide is very different and very unique from all the other messenger molecules. It's a gas. It's a free radical with an unshared electron in its outer shell, and therefore, by definition, is quite reactive. It wants to suck off an electron from another molecule to fulfill the dual electron shell in its outer shell, and therefore oxidize this other material. It's very lipid-soluble, and it can go wherever it wants. It can go into the nucleus, into the mitochondria, it can come out of the cell, it can influence neighboring cells. It can attach to various carriers and go upstream and downstream to be a hormone to regulate tissues at a distance. There is no messenger that has all of these diverse functions: intracellular, extracellular, a neurotransmitter, a hormone, an autocoid, a paracrine substance. We give it a lot of different names. When nitric oxide comes out of the endothelial cell, it can go over to the smooth muscle cell and regulate the production of another messenger molecule, cyclic guanosine monophosphate. And that then regulates the contraction of the smooth muscle. And I'll tell you the mechanism a little bit later. So while there are hundreds of first messengers, there are a modest number of intracellular second messengers, perhaps only 5 or 6 or 7. Every one of them so far has gotten a Nobel Prize. There probably will be a couple more to be found in the future, and they too, I suspect, will get Nobel Prizes, is my guess. Nitric oxide, I believe, is a very, very old molecule. In fact, some years ago, I wrote a very short review proposing that nitric oxide participated in the evolution of life. I wish I could do the experiment to prove that hypothesis, but I can't. I think what happened 4.5, 5 billion years ago, before there was oxygen on this planet, there were organisms in the deep crypts of the ocean, near the boiling magma that came out of the earth, that were somehow surviving in this toxic environment, and with evolution evolved in the earliest forms of life. The materials boiling out of the earth were transition metals, gases, hydrogen sulfide, carbon monoxide, nitric oxide perhaps. And these organisms figured out a way to survive in this horrible, soupy, toxic environment. But organisms are very clever. Once you develop the biochemical machinery, you can often, with evolution, adapt it in a positive way to not only detoxify substances, but to start using them as messenger molecules to talk to each other. And they began to feed upon each other, phagocytize each other, colonize with each other to form multicellular organisms. So I think it was a very important molecule in evolution. There had to be simple molecules early in life. They couldn't be complicated. And I think nitric oxide was one of the important ones. However, about 50 or 60 years ago, it attracted a lot of attention from the environmentalists when it was recognized